Okay, YouTube, in this video we're going to start to explore how to solve logarithmic equations. So that is to say, in the last 3 videos we've done, we've solved some exponential equations. In this video we're going to look at logarithmic equations. So let's go ahead and start by talking about what a logarithmic equation is and talk about how it's similar to solving exponential equations in the first place. So we say that a logarithmic equation, these are equations that involve logarithms of variable expressions. So that is to say that we may see something like log base 2 of x equals like 7. And what we're trying to figure out is what this x is right here. And so solving for that in certain instances involves a little bit more than what we guess could do here, which is rewrite it exponentially and be done with it. But here's the deal. We're going to be solving equations that have unknowns inside the log. And so the first property that we're going to look at in order to help us do this is what we call the one-to-one property of equality, or at least the property of equality for log equations. So we're going to say that this is the one-to-one property, but basically the one-to-one property says that if b, x, and y are all positive numbers, they're all real, and by the way, your base here, your base on your logs is not 1, then we'd say that the log base b of x is equal to the log base b of y if and only if x is equal to y in the first place. And so one thing that I want to mention here is this. If you're solving an equation that has a log on both sides and they're both base b, then one thing we could do is just go ahead and say, well then what's in here has to be equal to what's in here. We can go and start to solve by solving that. But also what we want to say here is that it kind of leads us to a pretty awesome result in terms of exponentiation. So I'll get to exponentiation in a second. Just to reiterate this again, let's say we had an equation log base 2 of x is equal to log base 2 of 7. The one-to-one property of equality says that because the left side's identical to the right in pretty much every way, then x and 7 would have to be the same thing. So we're going to look to use this one-to-one property of equality if we can set both sides equal to one another and they're both logs with base b. Otherwise, what we're going to do is we're going to use a technique called exponentiation. So we say that the preceding property implies that if we're given an equation x equals y, then we can exponentiate each side to obtain an equation of the form b to the x equals b to the y. This technique is useful for solving some logarithmic expressions. And so what I'm going to do is I'm going to kind of list these out here in text form, because I know that my handwriting is going to be really bad. We'll get this in a lot faster. But solving logarithmic equations. The very first question is this: can we write both sides as logs having the same basis? We'll say if so, then use the one-to-one property and set the inner log values equal to one another and solve. If not, though, we'll say if not, then proceed to number 2. And number 2, what we'll write here is this. Number 2, if, let's put it this way, isolate the logarithm. So just like we would isolate an exponential base, we're going to isolate the logarithm. The next thing we're going to do, though, is exponentiate both sides using the base b. And just to be clear on this, the same base as is on our exponent or exponential expression. So what we're going to do is we're going to put these kind of to use here, and still I haven't explained exponentiation, but let's go ahead and take a look at what I do mean by exponentiation. The thing that we're going to want to make sure that we write here is this. Exponentiation says that if we were to have two expressions like this, x equals y, and we know that they're equal to begin with, so we'll write given, okay? Then our exponentiation with base b is, the exponentiation of base b would be this. We'd say then b to the x equals b to the y. So that is to say that we put a base on both sides, and what we had initially in our equation, we make those the exponents of this thing that has the same basis. So you might recognize here, this is just the one-to-one property of equality for exponential things. But I'm sure that you probably didn't know that if x equals 7, that you're allowed to say then that 2 to the x equals 2 to the 7, and we wouldn't be lying. So if that's the case, then let's use these properties one-to-one and also exponentiation to help us solve some equations here. So looking at this first example here, in example 3, it says we want to start by solving this equation in A. So it says that the natural log, or log base e, or ln of 4x minus 7 is equal to the ln of x plus 5. So the neat result that we are led to here is that because both of these logs are on both sides of an equation and they both have the same basis, then we won't need to exponentiate, because this is true if and only if we could say therefore 4x minus 7, or what is inside of this log's argument, is equal to what is inside this log's argument here. So from this stage, what we could do is we could just go ahead and proceed by solving algebraically, saying that we want to get all of our x's on one side. Let's go ahead and isolate this by adding 7 to both sides here. I suppose, if 3x is equal to 5 plus 7, that'd be 12, then we would be led to the result that x is equal to 4. And so to check this, we could go ahead and plug this back in. We get the ln, I suppose I can't write on that, we'd say the ln of 4 times 4, which is 16, minus 7 is equal to the ln of x plus 5, which is 4 plus 5 here. We would get the ln really of 9 is equal to the ln of 9. So I'm going to proceed, through the rest of this video here, because I know that all of my solutions work out. With not checking my solutions, I would encourage you to do so. But let's look more at how we might solve an equation of this form. So looking at our second equation, I'm going to take this out here in purple. We have log base 2 of 5x minus 17, and this is all equal to 3. Now, because I noticed that there's one and only one logarithm here, then what I'm going to want to do is I'm going to want to isolate this log. Now, the next step would be to exponentiate both sides using the base b. And looking at this, we would say that our base b here is 2. So to exponentiate both sides, the way this is going to look is going to feel weird to do this the very first time. We're going to say 2 to everything on the left is equal to 2 to everything on the right. And so therefore we are led to this expression 2 to the third on the right has to be equal to 2 to the log base 2 of 5x minus 17. So now this looks bulky. But what I want to mention is recall that exponential things and logarithmic things, as long as they have the same basis, cancel out and are inverses of one another. So we say 2 to the power of log base 2 cancels out, and what we get left with is 5x minus 17 is equal to 2 to the third. Now, because I know 2 to the third, and it's not like 2 to the 13th, I'm going to go ahead and simplify that. So we see that 5x minus 17 is now equal to 8, and adding 17 to both sides of this equation, 17 plus 8 gives us 25 on the right side. Now what we could do is we could divide both sides by 5 here, and what we're led to is this conclusion that x is equal to 5. And so you can see by isolating the base, or isolating the logarithm, and then taking or exponentiating both sides, we could come up with some solutions for our equations here. So what I want you to do is try this on your own. Go ahead and pause this video and try these next two equations on your own, and then when you're ready to see the solutions, go ahead and unpause the video. Moving forward here, we can see that because the ln of this here and the ln of this, these are two logs having the same basis and they're equal, then we're led to the conclusion that the only way this is possible is if 7x minus 4 is equal to 2x plus 11 in the first place. So we're using our one-to-one property here. And so because we have this one-to-one property of equality, we can go ahead and finish solving this like we would algebraically any other time. We'll go ahead and add not 5, but 4 to both sides here, leading us to the conclusion that 5x is equal to 15, and so x must be equal to 3. Should have gotten 3 there. And on this next equation here, because we don't have a log on both sides, what we're going to do is we're going to go ahead and exponentiate both sides with a base of, looks like here, 2. So what we end up with here is this. We say 2 to the power of log base 2 of x minus 6 is the same thing as 2 to the 5th because of the one-to-one property of equality. So with our exponential thing of a base of 2 and our logarithmic thing of base of 2 here, being in that exponent of the exponential thing of the base of 2, those cancel out. We get left with x minus 6 is equal to 2 to the 5th. So now that's a little bit bigger, but I do know that 2 to the 5th is 32. What I want to say, though, I guess, is make this comment. If this, were like 10 to, well, not 10 to the 5th, 11 to the 5th, you can go get a value on your calculator, but for now it'd be easy to just leave it as 11 to the 5th. But for right now, since this was so small, we'll evaluate it here, and we'll add 6 to both sides. Looks like we get an x value then of 38 here is what you should have gotten. Cheers.